Bienvenidos todos, bienvenidos todas a la conferencia en el marco del XIII Coloquio de Estadística organizado por la Escuela de Estadística. I'm going to switch to English now. Welcome everyone. It is a pleasure to have you here with us today. Please allow me first introduce Dr. Christopher P. Saunders, who kindly agreed to participate in our event as a speaker. Dr. Saunders is from the Department of Mathematics and Statistics at the South Dakota State University at Brookings, South Dakota, USA. Dr. Saunders is a mathematician from California State University. He also has a master's degree and a PhD from the University of Kentucky, intelligence community from Johns Mason University, and he also has been a visiting scientist with the FBI labs. He is associate professor of statistics with tenure of the Department of Mathematics and Statistics, South Dakota State University from 2016 to the present. He has been an invited professor at the Department of Mathematics, University of Saunders, Summers 2015. He also has experience as a professor at the University of Kentucky. Also, he has been assistant professor or, signal processing engineer lead at the Washington Signal Processing Department. Also, associated research professor in applied information technology at George Mason University. Finally, he has been an IC postdoctoral research fellow of Document Forensic Laboratory at George Mason University. He has been referee for the Journal of Forensic Science and provides support to the FBI Research Laboratory as well as the broader intelligence community by reviewing and commenting on the statistical components of various research projects. He also has served on the Statistics Task Group of NIST OSAC in Forensic Science. He has also provided support to the latent fingerprint unit of the FBI Research Laboratory, among others. He has served as a member of a panel for the Division of Mathematical Science at the National Science Foundation. He has more than 20 published papers in important journals and more than 50 presentations and panels. One of them is entitled Strategies for Developing Undergraduate Data Science Program. It was presented at the Joint Statistical Meeting of the American Statistical Associations, Chicago, Illinois. Today, we have the honor and privilege of having Dr. Christopher Saunders as a speaker. Today's lecture is entitled An Overview of the Forensic Identification of Source Problem. Chris, in the name of our School of Statistics and our university, we are delighted to have you here. And I wish you the best during your presentation. Please be aware that questions should be asked at the end of the talk. Please formulate the question as possible in English. If you don't know English, please formulate it in Spanish, and I try to do my best to translate it. Okay? Let's welcome Dr. Saunders. Thank you very much.
Thank you all. Thank you, Professor Salazar, and thank you all for this kind invitation. It is a pleasure and honor to be here. So this is, and it's a pleasure to be able to introduce more statisticians and mathematicians to one of my favorite classes of problems I've had that I've been allowed to work on. Thank you again. This is introduction to forensic identification of source and related problems in statistical model selection. A large portion of this work is with my PhD student, Cami Fugglesby, my former PhD student, Danica Oman, who's now a professor at Iowa State University, and my friend, Cedric Newman. All right, let's see if I can get this to work. Let's see. So my collaborators on this work are Joanne Biscaglia from the FBI laboratories. She's a She was my mentor when I was an intelligence community fellow, and has become an amazing collaborator and friend since. Lion's share of actually all the novel work I've ever done has been with Dr. Balia. Josh Dietman, who's one of Joanne Biscalia's mentors and was a visiting scientist at the FBI labs. He and I were the ones that were collaborating together on the applied project that we'll use. If we have time, we'll talk about some of the work with Austin O'Brien, who was Cogswell's and my student at South Dakota State. Jessie Hendricks, she's actually Newman's MS student and my PhD student. And she's just finished her PhD and is now went and joined Josh at MIT's Lincoln Labs. And then Madeline Osborne, who was Cedric's master's student and Cogswell's PhD student. And so these are the collaborators and my friends who've worked on this project with me. Let's see, so an important disclaimer, and some of the work was done during the FBI Visiting Scientist Program, and this was administered by Oak Ridge. The opinions and conclusions that are expressed here are my own, and any mistakes or anything is my fault. And I'm an idiot, so I'm sure there will be mistakes, and they're all mine. This has also been funded by two grants, one that I was the PI on and led, and then another one that was jointly led by Dr. Newman and I from NIJ. And the opinions and recommendations here are also all my mistakes and do not reflect those of the Department of Justice. All right, now since the busy work is over, let's introduce a problem. So, or introduce the types of problems that we deal with in forensic science. So in forensic science, there's the common problem is the identification of a source of an object with an unknown source. So most recently, I've been focused on different types of objects that are recovered from an improvised explosive device. So, and for this talk, we'll focus on copper wire. So the first question is, did the copper wire samples found at the crime scene, which is an improvised explosive device has been recovered, are they the same as a wire coil, so a coil of wire related to the suspect? So say we find an IED, an improvised explosive device, at a various location, and then we have a person that we suspect may have been the person that released it, and or manufactured the explosive, and we find a wire coil in the suspect's house. Does the copper wire in the bomb, quote unquote, match the copper wire found at the suspect? So that's the first kind of class of problems, and those are really important. We tend to call those specific source problems. We have a specified source of the trace samples that we're recovering. Another class of problems is, say we have two improvised explosives. So say we have a bomb that went off in one area and another bomb that went off in another area. We now have our copper wire samples from each of these explosions. Does the copper wire look like it came from the same wire coil or two different wire coils? If it looks like it came from the same wire coil, that suggests that we have one person that's manufacturing these explosive devices, and suggests that we're not having to find a plethora of people that are manufacturing bombs. There's two third questions, which I don't think we'll get time for, but are very important. One would be, one is focused on who is the manufacturer or refiner of the copper samples found at the crime scene. So in this case, we have a large database of manufacturers of copper wire. And what we're trying to do is suggest who should be the suspect, or who should be the source, who's the suspect for these based off of just these copper wires. The fourth question is related to the third, except that we may not have an exhaustive list of the manufacturers of the copper wire. So for this talk, we're going to focus on questions 1 and 2, and based on, if we have time, if I go exceedingly fast, which based on my current time projections, I am not, we may be able to extend to questions 3 and 4. All right, so let's focus on the exact nature of the questions that we're talking about. So in general, when we're working on these problems, we're concerned with what is being asked by the practitioner. So usually I'm a statistician, I'm an expert in the interpretation and presentation of evidence. I will usually be supporting a forensic practitioner who's an expert in the analytical techniques, the manufacturing process, and the different science portion of forensic science. And so what'll happen is I will collaborate. I'll be sitting there and we'll have some important discussions and talk with the forensic scientist and maybe the decision maker about what type of problem they're working on. So typically we'll have two different types of questions are usually asked. The first one would be, are the copper wire samples found at the crime scene from the same wire coil found on the suspect? So in this case, versus the other common question we get is, well, it's becoming much more common now, but the other class of questions is, are the copper wire samples found at the crime scene, in two crime scenes from two different crime scenes, are these from the same wire coil or are they from different wire coils? Well, what's the difference in these questions? Well, for question one, the source, in this case, the wire coil related to the suspect, it's fixed. It's right there, it's sitting in front of us. And the question is how does that wire coil generate wire samples like what we found at the crime scene? It is fixed. Now, the second question is there's not a specific source in mind. We just have two, traces of copper wire, and we want to know whether or not the two samples share a common but unknown source. All right. So why is this distinction important? Well, there's a number of issues. Each of these questions can have radically different answers. In this example, I believe we get two different answers. We have values of evidence that favor, they get point in radically different directions just based on which question we ask. So there's a number of interrelated reasons why this is important. The methods that are used to solve the problem in an optimal decision theoretic sense have fundamentally different structures. The interpretation and presentation of the results of the identification process, these are fundamentally different in how we explain what we're seeing and how we present the evidence. The definition of what makes an error. So, and this is related to what we mean by an optimal manner. We also have the evidence that's used to answer the question. Usually we have different structures of evidence and different types of databases that we can use to talk about these questions. And probably of most interest in this session is the probability models that we use to characterize the evidence, the ways that we generate the data generating or evidence generating process. All right, so let's make this concrete, because even though I love my mathematical statistics and love to have pages and pages of equations, I find that I tend to personally get lost unless I'm thinking about an experiment on how things are working on, or how my data is arriving. So let's go ahead and talk about a specific case. So we'll talk about copper wire and analytical measurements. So the example motivation is an improvised explosive device known as an IED is found. A roll of copper wire is found at the suspect's house, and then the forensic statistician is presented with the following question. Is the copper wire used in the IED indistinguishable from that found at the suspect's house? And then the evidence that we're presented with, that we get to work with, is going to be decomposed in this way. So we have copper wire that's been dissolved into a solution. We cut 3 copper replicates. So imagine if you have a copper wire that's stretched out, you do 3 slices that all correspond to about 0.2 to 0.6 grams. We then remove the surface contamination with a 30% nitric acid for 5 minutes. This is then dissolved in a 70% nitric acid. We then use a microwave to break down the microscopic particles. And then we'll dilute this to about 1,000 parts per million copper. We then will use a ICP-MS, so an inductively coupled plasma mass spectrometry analysis. This is a standard method that's used in trace element analysis. We will then look at the 8 elements that were found in concentrations greater than the quantitation limit and consistently measured with good precision. So we'll use these 8 elements. 3 separate pieces of each sample were carried through the preparation process and analyzed in ICP-MS. The method is invalidated using all the 3 replicate measurements, or using a NIST certified reference material. All right, so that's how we get our actual measurements and what the numerical measurements are that we'll be looking at. Now we have to think about what the probability models are that we want to think about how this process is generated. So for copper wire manufacturing, first you have your mine. You then have a pre-treatment from the mine. There's then an initial refining process. Then you have electrolyte refining. And then you'll have cathode copper, which will be like these wafers, these sheets that you can look at. We'll then have a mine. So we then will break this down into sheets, tubes, bars, rods, and then which look like this. So this will be coils of copper rods. And then the rods then get stretched out into a wire. So now what we're going to be looking at is we're going to have variation in the trace elements that we look at between rods. Now the rods actually give us the different diameters we have. We'll have different diameters of wire that we look at. And so it'll be an exhaustingly huge amount of work to characterize the actual wire coils. So we're going to go back and look at rods, and we'll use the rods the different size of the rods would correspond to the size. So by using the same amount of each sample being of the size, by this mass allows us to do that number of that allows us to get an idea of what the sample variation would be on the wires. All right, so our sampling, so generally what we're going to do is we're going to use our discriminating power to make sure that we can actually discriminate between sources. So discriminating power is the probability of correctly determining that 2 samples randomly selected from a population are different sources. So we have 3 wires, which we sampled at every 5 feet, and then we'll use these we'll use this as our between source copper is 1 production sample every 90 minutes from the rods that we can use to get an idea of what the between source variability is. So these are the wire concentrations that we have for the 3 wires. So here's wire 1, here's wire 2, here's wire 3. And you see we have very nice separation between the wires on a number of the different elements. Now here's our rod sample concentrations, and this is giving us an idea of what the difference is between copper wires. All right, so the data sets, it's important to point out that these data sets are collected for an exploratory nature, and the purpose of their collection is to facilitate the study of the manufacturing process, and then with a focus on developing both the forensic analytical techniques and the statistical methods needed to support those. So the problem we have is we have a collection of 45 feet of 12 gauge copper wire, from which we have a collection of samples every 5 feet. We have a second collection of 20 feet of 12 gauge copper wire, from which we have samples every 5 feet. And then we have 93 samples collected from the rods. Now, what we would like to do is discuss the statistical and evidence interpretation aspects of how we address this question throughout the rest of the presentation. And we basically want to determine if these these two collections of copper wire from the same source. So this is just doing a pairwise scatter plot so we can see all of the data at the same time. So you can see we should have some red for our 5 samples. We should have some green for our green samples, and then we should have the blue samples are the copper wire rods. And so this gives us just an idea of what the variation and the multivariate nature of the data set is. All right, so within both the European and the American and the British legal systems right now, there's a very big focus on using likelihood ratios for presenting and interpreting evidence. And so I'll talk a little bit about the notation and conventions for these approaches. So these arose from a paper written by Dennis Linley, entitled A Problem in Forensic Science, and it was published in Biometrica the year before I was born in 1977. Now, the problem of deciding whether two sets of fragments have come from the common source frequently arises in forensic science. Material is found at the scene of a crime, and similar material is found on a suspect. Do the two come from the same source, thereby suggesting the suspect was at the scene, an example of which we will go through and refer to in this paper. Now, what's interesting about it is the mathematics that Linley solved out in this paper is actually for what we would call the common but unknown source problem, even though he's using it to make a decision about a specific source problem. So we'll talk a little bit about the differences between these. So Colin Aiken, Paul Roberts, and Graham Jackson have written for the Royal Statistical Society. This then was incorporated into the European Network of Forensic Science Institutes in forming and recommending that forensic science is basically the way we need to use Bayesian methods or extensions off of Linley's approach for all types of forensic science. All right, so the idea is what do we believe the likelihood of observing the evidence is under the prosecution model, and we compare that to what we believe the likelihood is of observing the evidence under the defense model. So in the Bayesian paradigm, our posterior odds are what we believe given the evidence, or what our decision maker believes given the evidence. The prior odds is what they believe the decision maker believes before they observe the evidence. And then the likelihood ratio, or the Bayes factor, is what the forensic statistician is responsible for calculating. This allows the forensic statistician or scientist to present the evidence in a very concise manner, or they can say the evidence is 100 times more probable under H sub P than H sub D. That is an incredibly concise and precise way of presenting evidence to an individual that's doing a decision, has to make a decision about what's going on. It allows them to combine that evidential value with other similar types of evidence values for different types of evidence. So say I have copper wire, say there's another thing where they have aluminum powder, they can combine the Bayes factors or the likelihood ratios from the aluminum powder with the likelihood ratio and Bayes factor from the copper wire, which allows them to get an omnibus likelihood ratio from two different forensic scientists just by multiplying the two together. That's an amazingly powerful thing. All right. I fear I tend to be very careful in trying to make distinctions between the inherent stochastic process for how the evidence has arisen, IDR statistical experiment, versus what probability measures are used for characterizing a belief or personal belief. Generally, if you're Bayesians, you look at me like I'm insane. If you're a frequentist, you also look at me like I'm insane, because who would use a probability measure for a belief? Anyway, so I'm going to use Fs to denote an induced probability measure. This is something that corresponds to an experiment, usually a sampling experiment, that characterizes how the traces or evidence arises. So this is the likelihood of observing the realized value of the evidence given the value of the distribution parameters characterized by a well-specified statistical model or sampling model. Pi is going to denote a probability measure associated with belief. So something like this would be my belief about the value of an unknown parameter given the evidence, and we'll usually refer to this as our posterior belief. Capital E is going to be the random variables associated with the evidence. So this is what, before the sampling experiments that give rise to the evidence are performed, we're going to think about those as capital E. The distribution of E will usually be specified by a class of sampling models for how the evidence has arisen. Little e is going to be a realization of the random variable associated with the evidence. So generally, in most complex evidence forms, the stochastic nature of how the evidence is characterized or generated is unknown, but characterized by a fixed parameter theta naught. The actual value of theta is not really of interest, and so it's a nuisance. However, it's necessary to estimate or at least characterize our uncertainty about the actual value of theta so that we can decide between the competing models for this. In this, I'm going to use a name and Pearson approach to estimate the likelihood ratio. This entails solving for values of theta that maximize the chance of observing E under the constraints implied by the prosecution model versus the constraints that are implied by the defense model. This is not a rigorous Bayesian approach. However, the name and Pearson likelihood ratio for the sample sizes that we're working with do have some nice properties that I'm confident would lead to an admissible decision rule. All right, so now a Bayes factor is interesting because this is the only approach that we actually know is an admissible decision rule. It is our belief about the likelihood of observing the full set of evidence under the prosecution model divided by our belief about observing the evidence under the defense model. A likelihood ratio is going to be only the actual likelihoods of observing those, and it's usually going to be indexed by our nuisance parameter. If we know or are certain what the value of the nuisance parameter is, then we have a likelihood ratio of this form. So generally, if you're using something like a Jim Berger's approach, we would have for Bayesian statistics, this would lead to, you'd usually write this as the marginal likelihood of E given the prosecution model. We can usually calculate these by these marginal distributions by Monte Carlo integration, which turns out to be usually technically difficult. The name and Pearson form basically takes a form where we find the value under the constraints for the prosecution model, and we look at the maximum value versus the constraints under the defense model, and we look at the maximum value. And then we compare those two maximums. These are really interesting types of likelihood ratios that actually show up a lot in machine learning and pattern recognition problems when you have small values, when you have small training samples per class, but large number of classes. There's some beautiful write-ups in McLaughlin's Introduction to Statistical Pattern Recognition, or Seeber's Introduction to Multivariate Statistics on these classes of methods. Really older versions of T.W. Anderson also talk about this class of methods, although he refers to it as a minimax approach to classification or machine learning. And so, at least from my point of view, it's a little bit harder to follow. All right, so why would we want to use a name and Pearson likelihood ratio in place of a Bayes factor? Well, this integral to calculate the marginal or approximate the marginal likelihoods is hard. This is typically one of these things where this is just a hard integral to calculate. And typically what will happen is under the prior model, either the marginal is close to zero, but one of them is zero. It can lead to very unstable estimates of the likelihood ratio. Sometimes we'll calculate these on a log scale, which then it becomes questionable whether or not anything besides just the first moment exists on a central limit theorem. So you may have a strong law, but not much else, like a central limit theorem. And so these are very hard and technically difficult Monte Carlo integrations that you have to worry about. Dr. Oman has solved out, so if the second moment exists for these marginals, Dr. Oman has, for her master's thesis, or master's paper, spent a fair amount of time solving out for what the standard error is of these. The thing to notice is that you get one of the marginals on the standard error comes into the denominator squared, which can make really large variances if this is if the defense model is the one that has the small probability. So when we're in a situation where we want to talk very precisely about whether we should grab, say, Professor Salazar and measure the evidence against him, that's when this computational likelihood ratio is most unstable. So that's problematic. Typically these can be incredibly wide and difficult to focus on. Well, is the name of Pearson reasonable approximation for the Bayes factor? Well, it does depend on what type of identification we're trying to perform. It also depends on the amount and type of information that is contained in E, or in our evidence. If we have time, we'll talk a little bit more about this. Dr. Oman and I have a recent paper that was just published in Statistical Science where we go into all of the gory details of this if you're interested in the work. Well, let's talk a little bit about factorizing this. Well, so for specific source, there's a typo. That should be question 1. We'll talk now about the specific source approach to identification of source problems. There's generally 2 broad classes of approaches. I have been focusing on likelihood-based methods, and those are currently where most of the research by statisticians are taking place, is on how to calculate these likelihood ratios. These methods are done by statistical inference and model selection-based approaches. The method used is going to depend on the interpretation of this. So sometimes people will use a 2-stage approach, where they'll say, can I exclude the specific source as giving rise to the evidence? And if not, they'll look at some rate at which they would be able to exclude alternative sources, versus the Bayesian approach. We're going to focus on the Bayesian approach for this talk, for the moment. And then error occurs if wire samples are implied to have come from the specific wire's coil of interest, or when they are not from that wire coil, and vice versa. And so, but the important thing to notice is that the error is always with respect to a specific source. So every time we're going to be doing one of these problems, when we're talking about the performance of the system, we need to be able to talk about the chances of making mistakes or our accuracy with respect to the case at hand. So evidence, well, we've gone through the evidence. We have wire samples from an unknown source, and then we have samples from the specific wire coil, and then we have a sample of sources in the background population. We do need at least 2 probability models. We need a probability model for how the specific wire coil generates evidence, and then how an alternative source population of wire coils generates evidence. So for our statistical models, we're going to assume that the wire samples from E sub u came from a specific wire coil in question. In H sub d, the wire samples from E sub u came from a randomly selected wire coil in the alternative source population. Since wire coils are manufactured from copper rods, we will assume that the alternative source population of wire coils can be characterized by studying the distribution of samples of copper rods at the manufacturing facility. It's a big assumption, and we'll just have to make it. So again, going back to our pairwise scatter plot, this is our full set of evidence that we're looking at. Here it is again, just I've used an LDA rotation to maximize separation between all 3 groups. So this is going to be an artificially large separation between our 5 trace coils, our 10 samples from the control sample from the specific source. So again, we're going to focus on this calculating the likelihood ratio. we have H sub P is the recovered wire samples came from the specific source, and the recovered wire samples did not come from the specific source. And we're trying to make a statement along these lines. The evidence is 100 times more probable if the specific wire coil in question is the source of the recovered wire samples rather than a randomly selected wire coil in a relevant population of wire coils. So we have our evidence, and we can partition into 3 sets. We have E sub S. These are our elemental compositions on 10 wire samples from a specific source. E sub A is composed of elemental compositions of 93 samples collected from a population of rods that were used in constructing the wire coils. And then E sub U is the elemental compositions of 5 wire samples from a second wire coil. All right. So here is our evidence with the unknown source. So these are our 5 wire samples. Here are our 10 control samples from the specific wire coil. There's E sub S and E sub U. So those are pretty far apart based on this LDA rotation. But remember, this LDA rotation is designed to maximize separation between the 3 classes of evidence. Here is E sub A. This is the background variation for between sources. And then this is our complete set of evidence. So under H sub D, we have 2 different wire coil. We have 2 different sources where we have this block where these guys are actually from different sources. This is our control sample. This is our within source sample. Now from our H sub P, we're going to assume that we have a really wide spread between for our within source variability. All right, so we're going to use a Y sub S is going to be a multivariate vector, and so Y sub Sj is going to denote the set of measurements on the jth wire sample, and we'll have 10 of those, and that's going to be from a specific wire coil, and we're going to assume that that's a multivariate normal with a mean mu sub S and a covariance matrix sigma sub S. And then we'll let theta sub S naught is going to be the true data, the true mean and covariance for that wire coil. E sub A is interesting. This is going to be just a traditional simple random effects model where we'll have Yij is going to be the jth measurements, is going to be the vector of measurements from the jth wire coil, from the 8th randomly selected wire coil, and we'll assume that A is equal to 1 through n. There should be an A here, sorry about that. And what we'll have is just a overall mean for the wire coils in this population. And then we'll have a deviation for the ith wire coil, and then we'll have a ijth deviation for the jth sample of the ith wire. So these are all going to be multivariate normals, and we have 2 levels here. We have an overall mean for the background population, and then a between wire coil variance. And we'll have a theta sub S, which is going to denote our sigma sub S, which is going to denote our within source variability, the deviation of the samples from the wire coil around the sample. Unfortunately, we don't have wires, we have rods. And so we're going to actually have a model where we're just going to assume that the rods, we have an overall mean for the rods, and then we have a deviation from the jth rod. So we're going to make the assumption that the mean of the rods is equal to the mean of the wires, and that the between source variability for the rods is equal to the between source variability for the wires. This is a strong assumption. I don't have the data to test it. This is basically what we have available, and we have to get an answer. So this is how I'm going to try to solve it. So now if we return to our name and Pearson likelihood ratio, we can define this as this max, where we have our max of theta S, where we look at the joint likelihood of E sub S and E sub U if they both came from the specified wire. And then we have our max of theta A over this. So notice that E sub u is entangled with E sub s for estimating the specific source parameters. Now in the denominator, we now have E sub u gets entangled with theta sub a. So E sub u contributes to the estimation of theta sub a in the denominator. Well, we can go ahead and we can solve out for the block matrix of what the covariance matrices are and then stack the means in such a way. Excuse me. We can then use remote estimates to estimate theta sub u, or the mu's and means, and then we get a likelihood ratio of very small, which is effectively 0, which means we're really certain they did not come from the same source or the specific source. Well, we can then factor the likelihood ratio, which is nice for the specific source, where we basically estimate our parameter using the entire set of evidence and assuming the defense model is true, and then we integrate the likelihood ratio with respect to our posterior distribution when we assume the defense model is true using the entire set of evidence. That's a really stable form of a likelihood ratio that Dr. Oman figured out, and it's really nice for this class of problems. We've also used a class of problems where we use a Bernstein-von Mises approximation to the posterior distribution, and then use this as our integrals for being able to solve this out. Dr. Oman's dissertation goes into exhaustive details about this and can talk about the difference between these. Again, this is summarized in the more recent statistical science paper that we just published. There's another approach, which is the two-stage approach, where if we take the wire samples from E sub u and the defense, so the approach is to compare the wire samples that make up E sub u and E sub s with a Hotelling's t-squared statistic, and then we exclude or cannot exclude. The p-value for this test is effectively 0, so we would exclude the source of E sub s as the source of E sub u, and we would stop. However, if we had failed to reject, we would look at the conditional match probability, where we would look at the chance of a randomly selected source matching E sub u, or the chance of a randomly selected trace matching E sub s, and it's unclear which one we would be interested in. For the common source, a common source problem, we now, instead of having a fixed source, we have two sets of traces. We assume that we have a randomly select, do we randomly select one wire and then do two samples of traces from it? Or do we select two wire coils and do a simple random sample from it? And so in this case, we'd have E sub u1 and E sub u2. E sub u1 is going to correspond to our 10 wire samples. E sub u2 will be our 5 wire samples. E sub a is going to be our same 93 samples. So this is a restating of the problem where we have E sub u and E sub s came from the same specific wire coil versus E sub u came from a randomly selected wire coil. Now the common but unknown source is going to say that E sub u1 and E sub u2 came from the same randomly selected wire coil in the alternative source population versus they came from two different randomly selected wire coils. That randomness changes some of the nature of the models that we're doing. So we now have this, we're using this hierarchical multivariate model now. It's just a question of whether we drew n plus 1 wire coils at random from the population, or do we draw draw n plus 2 randomly selected wire coils in the population. We'll make the same assumptions about wire coils as rods that we made for the specific source model. And now when we calculate our Neyman-Pearson likelihood ratio, we have a likelihood ratio of 20,000. In effect, in this context, we are reasonably certain that E sub U1 and E sub U2 share the same common but unknown source. So what's happening here is E sub U1 and E sub U2 are actually far apart. However, this mean, their average. So we have two very rare, we've randomly selected two very rare sources. However, the mean of them is less rare than either of them. And so in effect, that leads us to a name and Pearson likelihood ratio that's pointing in the opposite direction for the common but unknown source setting instead of the specific source. And it's really important to note that the only difference in these two questions is whether whether we randomly selected the wire coil or if it was a fixed wire coil. And so this is one of the problems with this likelihood ratio based approach. If we were to do a two-stage approach, we would get similar answers for both of these. I went ahead and did a simulation based off this data, so we can see that we do get variations between these. And what we have is the specific source log likelihood ratio versus the common source log likelihood ratio. And what's happening is we're basically in somewhere around this region here. And we've just had a really strange happenstance. I mean, it happens from time to time. You can see that these are related to each other. It's just that they're not exactly the same. If they were, they would lay perfectly on this red line. We can do a similar factorization that Dr. Noman did. The two-stage approach is actually really strange for a common but unknown source. Again, we just do our first stage is the same. We could do a comparison with our t-squared statistic. You may be able to do a shrinkage estimation problem where we talk about a average t statistic instead of a one that's invariant. So, it's an interesting problem. If we fail to reject the null, we just look at the chance of E sub U and E sub U1 matching by chance with respect to the comparison procedure. So for this case, we say same randomly selected coil and go from there. I'm going to skip Cammie's work because I think I'm out of time. And talk about some conclusions. So, well, which question does it ask? Well, it depends who you are in the process, depends on what you care about, and it also depends on what you're trying to do. It also really depends on evidential resources that you have at hand. As an example, I tend to usually be concerned with whether or not we should be interested in a given suspect. So almost always I tend to default to thinking about specific source problems. This implies that all of my inference about the source of the unknown samples is relative to a given suspect. Everything I'm doing is building up my inferential structure about a specified suspect. And I tend to focus on this. Did this specific source generate this trace? We do want to be careful and aware of Linley's paradox. This copper wire example is an illustration of the phenomenon known as Linley's paradox. This wasn't an exhaustive search to find it. This just occurred naturally in a problem I was given for asking the question with the specific problems. It does occur in common source attribution problems when E sub U and E sub S are far away from the center of the alternative source population. This is the first time I encountered the problem without methodologically creating the data sets, basically doing exhaustive searches to run into the problem. Glenn Schaefer has studied this paradox in a large number of settings, and in most situations, the common source and specific source likelihood ratios will act approximately equal to each other, but not always, and that's important to be aware of. So why use a Bayesian method at all? Well, for this approach, I completely failed to use a Bayesian approach for the common but unknown source problem. My Monte Carlo error was incredibly extreme. And when it's reasonable to think in terms of variances, statisticians' beliefs concerning nuisance parameters tend to be embedded in the calculation. And Linley's paradox is something that shows up from time to time. I tend to, if I have to defend a Bayes factor, I tend to say that practitioners are comfortable with the thought process and statistics when a likelihood ratios are reasonable. In addition, decisions based off of a Bayes factor are admissible decision rules. Formal Bayesian approaches tend to be intractable when we do not know the alternative source population characteristics with some complete certainty. All right, and thank you very, very much. There's a lot more work. You can read about Dr. Omen's dissertation. And in particular, has a pretty exhaustive block of work. And let me pause and see what questions you all have.
For your magnificent presentation is a good example of what statistics can do to help society solve criminal cases, among other possibilities. We have some questions. In there, it says you can formulate your question in English at the end. And at the end, he will answer them. Let me switch to Spanish. ¿Alguien tiene una pregunta en el público para el profesor Chris? It seems that we don't have any question.
Well, I'm sorry. I'm sure I'm not used to talking. I'm sure I won't. Thank you kindly for bringing me.
I do have a question. How many times how many times have you used these methods successfully? I mean, when you try to find a pattern to see if somebody had made a crime, have you been successful with it?
So the role I tend to take is I tend to develop the algorithms that are then deployed by the groups I support. And so typically, so Dr. Omen has presented or has used the likelihood ratio approaches for problems that she's been working on. I actually tend to default back to using the two-stage approach. So I'll use something where can I exclude the suspect? And those methods have been used ubiquitously. Some of the systems that we've used for handwriting have been used. It is a very scary situation because you're writing out the algorithms and the code to do this interpretation and having it generate automated reports where you usually do not have access to be the person checking to make sure everything's reasonable. And so the answer is I don't know, but I do know the methods are being used and people keep coming back to me asking them to develop new algorithms for new types of data.
That's good. It seems to me that these methodologies you have been developing have a lot of potential outside the crime scenes and other investigations. That's pretty good. And you rescue the importance of statistics in these modern times when everyone is talking about only machine learning, artificial intelligence, and so on. People think that that's the only way to solve problems, and it is not. With the statistics, with sound statistics, and sometimes with simple statistics, you can solve effectively a lot of problems. And you have shown us that that is possible. I know you, and I know how much do you love statistics. You are very passionate with it, and I am amazed with that elegant word you have been developing.
So Professor Salazar, I believe you're saying that my statistics are simple.
No. Sound. I say sound. It's not simple at all. It requires years to reach that level, man.
So there's actually a very interesting relationship. So I have no idea what artificial intelligence means. It's a buzzword that's used arbitrarily to talk about anything that's quasi magic or complex, in my opinion. There is no machine learning. I have a much different opinion of. I actually have a lot of respect for machine learning algorithms, and I tend to think of so a lot of my training after leaving the University of Kentucky with you was I was actually retrained by the intelligence community in machine learning and interpretation and presentation of evidence.
Nice.
I tend to think of machine learning as adaptive, as model selection problems, and that it's right, and the type of problems that I tend to deal with are right there at that boundary between predictive analytics and machine learning, as well as very formal, rigorous decision theoretic mathematical statistics. It's right there at that boundary. And if we just had more, so like my training samples, if I had 10 training samples for my source, if I was going to think of this as a machine learning or classification problem, that's not a big data problem. If you fit like a neural network or a multi-level neural network or deep learning algorithm, you're going to get complete separation. The algorithm's not going to converge in any meaningful sense, and you're just not going to even be able to get an answer with sample sizes of this problem. Generally speaking, forensic science, the problems you have, if you're going to approach them as a machine learning or classification problem, you have a very large number of classes with very few samples for each class. And so any of the methods that are coming out of the kind of the computer science community are completely useless for this class of problems. And you really have to go back and think carefully in terms of your mathematical statistics to be able to come up with any type of answer, even if the results look similar to large-scale machine learning problems. In fact, most of the people that I trained at George Mason on these problems have all been recruited to go back to the Bay Area or on the East Coast and work in, say, Apple and Google as senior level data scientists and machine learning or artificial intelligence experts, just because the class of problems that they work on is really important in those areas and nobody's trained in those methods anymore.
Thank you. I have one last question. What did you recommend for the new generation of statisticians? We have a lot of youngsters here that are willing to learn not only statistics, but also data science. What do you recommend to them to learn, to be prepared to the new problems that will arise and are arising now?
It depends on how comfortable they are with statistics or with the foundational mathematics that go into it. Generally speaking, if they're comfortable with, well, say Dr. Griffiths, a major theoretic probability, I would actually say go and do a very classical mathematical statistics PhD, like the education that you and I received. Once you get to the point where you're talking about approximation theory and empirical process theory, then the mathematics for the foundations of machine learning and mathematical statistics are exactly the same. It's just a slightly different jargon that you use, and so you can get there. And definitely statistics, mathematical statistics programs, they provide, they have a more established and well thought out process for being able to get students to that level. If the students are not comfortable with major theory, and heaven knows I wasn't, I killed myself trying to pass Dr. Griffith's courses. You can actually go back and you can pick up a really beautiful experimental version of the knowledge by focusing on bootstrap methodologies and cross-validation and the different resampling methods, and building up from that point of view. And then statistics is either the most mathematical of the sciences or the most applied of the mathematics. And if you're comfortable with the science and the experimental methods, doing large amounts of simulation, large amounts of bootstrap methodologies and things like that, where you can do empirical experiments to build up that intuition of what will work well in given situations, is the other approach. I tend to teach my PhD students from the heavy-duty major theoretic side of these problems, and I tend to teach my data science master's students from the scientific experimental processes. And either one do really well. They'll have slightly different approaches and they'll have different expressions, but
okay, Chris. We thank you again for having you here, and we hope to see you soon.
okay. Well, I can't wait to see you guys. Miss you.
Okay, keep in touch, my friend. Take it easy.
Thank
Bye.
you guys all.
Bye. Gracias a todos.